Good evening, everyone. Can you hear me okay? Well, thank you. Thank you so much for coming out tonight. I know there's a lot going on, so it means a lot that you came to see the presentation tonight. My name is Janine Culligan. I'm the director of the Eleanor D Wilson Museum. And thanks again. Just one rule, if you have a phone, please silence it now. But I want to let you know that after the talk, there will be a reception out in the lobby, and I hope you'll join us for that. Also, the museum will be open, so you'll be able to see the exhibit. Also, I want to just mention that Dr. Stephen Wassell has made a number of videos that kind of go along with the exhibit. So in the gallery, there's actually a QR code that you can use with your phone and get to the videos, and they're well worth the watch. So I'm going to give a brief introduction and a brief bio of each of our speakers, and then turn it over to them. So Mark Reynolds has worked with graphite, pen and ink, watercolor, pastel, and other drawing media for over 60 years, developing interpretations of principles found in Euclidean and philosophical geometry. The exhibition, A Marriage of Art and Math, artwork inspired by dual Platonic solids, which is on view through April 23rd, consists of drawings and watercolors recently donated to the Eleanor D Wilson Museum by the artist. These are part of Reynolds' decades-long fee series of artworks which involve geometry of the golden section. They utilize a discovery made by former Hollins University Associate Professor Dr. Stephen Wassell that involves relationships found between two of the 5 Platonic solids, the dodecahedron and the icosahedron. Tonight's talk is a conversation between an artist and a mathematician. The two have been collaborating for almost 18 years, and it's a fascinating story, really an amalgamation of numbers and lines and color. Both are interested in how art and mathematics intersect, whether it be the mathematics found in everyday nature or the human body, or architecture and drawings. The two have written extensively about this dovetailing of art and math. Many of their articles can be found in a notebook that's in the gallery. And I want to thank Steve Wassell for being the instigator of this project and for making me think about presenting a math-related exhibit. And for those of you who are math majors, and I think there are a lot of you here, it's always like quite the tug to get you into the Visual Arts Center, so we're very happy that you're in here. I also want to thank Mark Reynolds for his patience with a non-math-minded curator and for his generosity in donating these works to the Eleanor D Wilson Museum. I also want to thank, as always, the museum staff, Laura Jane Ramsberg, Laura Carden, and Janet Cardy for all they do. And I also want to thank Eva Green. Unfortunately, she has a class right now, so she can't be here, but Eva was our January term intern, and she helped to frame, and she also transcribed all of Mark's little tiny graphite notes on the drawings into a label that's a little more legible. I also want to say that this program and its associated exhibition are funded in part by the City of Roanoke through the Roanoke Arts Commission, and we thank them very much. So I'm going to give a little brief, if you can stay with me for a little bit more. Before I turn it over, I want to give a very brief bio on each of them. Dr. Stephen Wassell received his BS in architecture from UVA, a master's degree and PhD in mathematics from UVA. There's a pattern here, as well as a master's in computer science from UVA. He was a visiting professor of mathematics at Randolph-Macon College and UVA, was a math professor at Sweetbriar College for 25 years, is that correct? And then in 2017, 2018, he taught at American University of Malta. And from 2018 to 2021, we were lucky to have him here at Hollins University. He retired from Hollins in 2021 and moved to Florida, and is about to move to Spain in a few weeks, so we're very happy that we could get him here before he leaves the continent. let's see, in 2012, he was selected by the Princeton Review for inclusion in the best 300 professors in the United States. That same year, he wrote an article along with an assistant for the Fibonacci Quarterly. I think that's something that everybody reads every day, right? And the article was titled Edge-Length Ratios Between Dual Platonic Solids, a surprisingly new result involving the golden ratio, which really is what started this whole phi series that you see in the exhibit. And now I'm going to turn to Mark Reynolds. Mark Reynolds is an artist, I don't even know how to say this exactly, geometrician? Is that correct? That works. And educator. He holds bachelor's and master's degrees in art and art education from Towson University in Maryland. He received an Andalot Fellowship to the University of Delaware for postgraduate work in drawing and printmaking. Additionally, Reynolds taught courses in geometry and philosophical geometry to graduate and undergraduate classes at the Academy of Art University in San Francisco for over 20 years. His work is represented by Pierogi Gallery in New York. He has had 12 solo exhibits across the country, the last 3 with Pierogi Gallery in New York. Those were in 2013, 2015, and 2018, and has participated in almost 100 group shows in California, New York, and Maryland. His work can be found in museums and public collections, including the Achenbach Foundation for Graphic Art at the Fine Arts Museum in San Francisco, the Leonardo da Vinci Library in Vinci, Italy, the Crocker Art Museum, and many others. He's also in a number of public collections, AT&T, Black & Decker, Citibank, Marriott, Warner Brothers, and again, many others. But enough of that background. Now we're going to start the conversation, and so please help give a nice warm welcome for Steve Wassell and Mark Reynolds.
Well, thank you, Janine. That was very kind, and thank you again for attending tonight. Delighted to see so many faces in the audience. And the original plan was to have this slide presentation for maybe 20, 25 minutes, but I've asked Mark if he wants to jump in at any time to do so, so maybe we'll have a conversation in the midst, but at some time we'll get Mark involved in the conversation and questions from you all as well. So, and if you have questions anytime, please shout out. At the end we'll have a microphone to pass around, or if you need to ask a question. I didn't practice this step. Let's see, how do I?
You might have to
click. Hit the space bar. I've got arrows, I've got enter, to space bar. I hit space bar. Oh, Gabe knows. That's all right.
I'll just have to switch back to that window.
Okay.
Yeah, there we go.
Thank you.
Then it should, yeah.
Okay, great. Thanks, Gabe. No problem. Okay, so first, a little background. You already heard this first bullet about Mark. He was also a longtime contributor to the Nexus Network Journal. Now, the Nexus organization has the Architecture and Mathematics conferences. The journal is the same theme. And he was a longtime contributor. He wrote the Geometer's Angle column. And we met through the Nexus organization. And you saw or heard already that the Pierogi Gallery represents him in New York City. And after his second show there in 2015, there was a review in the New Yorker that acclaimed the exquisite drawings of this San Francisco-based artist who, armed with straight edge and compass, transmutes the mysteries of geometry into dense meshes of colored lines, alive with spiritual intensity. This reviewer really got it, and in fact, I talked about this a bit in those videos Janine mentioned, and certainly check those out if you want to get more information. The basic idea, just very basic, is that Mark likes to find relationships between rectangles of various length to width ratios in his artwork. And other shapes as well. But so here's an example. This is in the square root phi series called Meanders from 2013. All of these are watercolor and pen and ink on cotton paper. This is the same series, square root phi series Spiral, same year, 2013. A newer one from the Thales series, and this is the one that we've been working on a lot for the last several months. Not this piece, but the Thales series, all the great mathematics behind it. So this is 2019. 2020, here, also the Thales series, the CQ subset. The last two are going back in time a bit. I mentioned these a little bit in the videos. This is the mu series, so the rectangle here, the overall rectangle is a mu rectangle. That's the name he gave it. This is Tulpa 20, 2011. And from the phi series, this is Galileo's Dilemma, 2011 as well. You see the circle and the ellipse there. And then a little bit about me. I guess you heard a lot of this already. I also worked with the Nexus Network Journal. And in fact, the last issue that I was a guest editor for just came out this year. Probably the most important book I've published is this one with Branko Mitrovic on Andrea Palladio's Filocarnaro. It involved both architecture and mathematics. We've actually been collaborating for quite a long time. We have these dual articles in the 2001 Nexus Network Journal that you see there. And often he'll have a construction and want to know if it's exact or not. That's where I come in at times. And then more recently, the work that you see in currently on exhibit here at Hollins is corresponding to this article here. And so that was our first Bridges publication. Bridges is the big annual art and math conference. And then the reason that it's pertinent now is that Mark just donated a lot of these pieces, 13 pieces in all, to the Hollins Museum, the art museum here. And then in attendance at that talk in Bridges was the editor of the Journal of Mathematics and the Arts. And she asked us to submit an article to that journal. So that's what that one is from, 2019. Just a couple more here. Another Bridges conference proceedings. This was last year on the Thales theorem, Thales series. And then we just submitted this last week to the American Mathematical Monthly. We'll see if that gets accepted or not.
Fingers crossed.
Fingers crossed, as Mark says, yes. Okay, enough of the outline. So dual Platonic solids, what does that mean? If you've seen the exhibit, or if you do see the exhibit, you'll see those two red and blue images at the back. That's actually tape on the wall. Great job by the museum staff to put those images there based on our drawings. So what are those trying to depict? This article was mentioned by Janine, a former student at Sweetbriar, Sam Benito. She goes by Sam, and she asked a great question about the edge length ratios between dual Platonic solids, and that's quite a mouthful, but I'll try to explain what that's all about. And it was based on her research in the senior seminar. So it's really cool to have a publication with a student, an undergraduate student, in a fine journal like the Fibonacci Quarterly, which I know you all read all the time, as Janine said. Okay, so Platonic solids, there are 5 of them. You see them here. And the ones we're interested in for this talk are on the left and the right, the icosahedron and dodecahedron, having 20 triangular faces on the left and having 12 pentagons for faces on the right. And these
They nest.
they can be nested. So yes, I guess actually one reason that Sam got into this is because she had taken a course in geometry, and I mentioned that at the end of Euclid's Elements, the 13 books of Euclid's Elements, he shows how to inscribe all 5 of these in the same sphere and then compares the edge lengths. And she said, well, how about the dual Platonic solids? And I was like, oh, well, I don't know about that. So asking the right question is very often a big part of the research process. So they pair up in duals, and that's kind of strange because there are 5 of them, but the tetrahedron is its own dual. So here's what it means. Okay, so let's look at the left figure. That's obviously a cube on the outside, octahedron on the inside. So the way that works, if you take the center of each face of the cube and then connect those adjacent centers, you'll get the red octahedron. And the same thing is true for the second one. So there's a face, there's a center. You can see where that makes one of the vertices of the cube, and you can probably see the other ones as well. So those two are what we call vertex to face pairings, because the vertex of one's on the face of the other. On the right is an edge to edge pairing. So look at those edges. And those edges, they're overlapping and they're perpendicular bisectors of each other, okay? And that's true as well for the dodecahedron and icosahedron. I'm not gonna go through any more animations like that, but you can sort of see what's going on. And then the tetrahedron is its own dual, so there's only one vertex to face configuration in this case because it's the same shape, and then the edge to edge pairing. Okay, so then if we look at the ratios of the side lengths of these objects in the edge-to-edge pairings, of course, it's 1-to-1 for a tetrahedron because it's the same object. It's 1 to the square root of 2, so this is the blue to the red. So the cube, the length of the cube's edge to, which is in blue, this is the center drawing we're talking about, and then the length of the octahedron's edge in red is 1 to the square root of 2, and then on the right, it's 1 to phi. And these 3 ratios are 3 of the most important ratios in the art math world. And again, you can watch the videos to see that. Mark might have some comments on that at some point. But so those are some really potent numbers there. Those were all well known. Vertex to face just so happens that the smaller tetrahedron has 1/3 the edge length of the larger one in that case. And then there are 2 possibilities with each of the other, because one can be on the outside or the inside. So 1 to the square root of 2, square root of 2 to 3 as well. And then this last one, on the right, that was unknown or it was incorrectly given in 2 sources that we found. So we think we're the first people to discover that answer is phi over 3, the golden ratio over 3. So that's what the article was about. So knowing that Mark loves working with ratios, I sort of challenged him, hey, take these 2 ratios and see what you can do with them. And he came up with some great stuff. So that's now getting down to exact geometric relationships. Okay, so back to those. Mark often thinks in terms of a decimal approximation, so you know decimal approximations for scores or maybe even hundreds of different ratios.
At least.
And so he found these 2, and then something I didn't do or didn't think about, he inverted them and found those 2. And those are approximation signs because I've approximated them to the nearest 4 digits, but it's really exactly true that those last 2 are off just by 1. So right away he discovered something I hadn't even seen before, that the ratios you get from these objects, if you take rather than taking larger to smaller, the top line, take smaller to larger, and, rather than take inside to outside, the top ones are inside to outside, take outside to inside, and you get 2 ratios which are off by 1, exactly 1, which is pretty amazing. And the way that you can visualize ratios is with rectangles, and that's what Mark does. That's his bread and butter, really. And so these 2 rectangles are exhibiting those ratios. Mark has always taught me that in the art world, you always talk about height first and then width. So height to width on the left, obviously it's a smaller height than width, so that would correspond to the point 8541. And on the right, obviously the height is bigger than the width, that corresponds to the 1.8541. And those 2 rectangles he then worked with. Did you have anything to add yet?
Only that the rectangle on the right that you see, for any of you that know the golden section, that's 3 golden section rectangles stacked one on top of the other. And tradition says that Corbu, the architect Le Corbusier, that's the profile of the United Nations building in New York. We all have something in common, and that is where our navel is located in relation to our height. It's about the golden section of our height. And we believe that Corbu actually used that ratio for the golden section. He has 3 of them. Remember, this is a United Nations building, so everyone in the world is being addressed by this. First one's physical, second rectangle's mental, and the third one up is spiritual. And that's one way of using the golden section and ratio, symbolically and spiritually. So, thank you.
That's a great segue. So one thing he found, well, first of all, the fact that the 0.8541 plus 1 is the same as the 1.8541 is seen geometrically by the fact that if you add a square, 1 is the length to width ratio of a square, right? 1 by 1. So if you add a square to the left rectangle, you get the right rectangle. So that's a geometric visualization of that fact that you see there. And then, as he said, I think this is next. Yes, the right one is 3 golden rectangles stacked up. Okay? And so then, he worked with those shapes, and he often calls his series or his pieces by the decimal. So the 0.8541 is an example of that. So first, this one, and this is in the collection here, up on the wall right now, the beginning of 4. Again, watercolor, colored inks, graphite, and cotton paper. And this is 2015. It's part of the 1.1708 series. So it's actually it's the left rectangle, but flipped 90 degrees. So therefore, it's a larger height and width. So it's a 1.1708 series is what we have here. And so what the decomposition of that, or the basic geometry, you've got a golden rectangle on the left and the right up above, flanking a square. Same thing below. You've got a golden rectangle in the middle, and those leftover pieces are also squares. So some lovely geometry there.
Can I interject?
Yes, please.
The arrangement that you see isn't the only possibility that's there. I mean, these pieces can move around in a myriad of ways, and it allows a designer, an artist, whomever, to be able to compose in a variety of ways, and every one of them that has a strength to it based on number that we find in geometry. So we have what's known as a square root of 5 at the top and another one below, but Steve just took it a little bit farther so that you can see farther divisions. But each one of those yellow golden section rectangles that you see in the corner are made from a square and a golden section rectangle. So these pieces can be further subdivided into smaller parts if they're needed in whatever you're designing or working with. And it leads to a lot of discovery, a lot of invention, a lot of fun, just to see what happens if I do this instead of that, and see what you may come up with on your own. I mean, it sounds serious, but another way to look at this is to see it as a way to play with really beautiful shapes in a variety of ways and enjoy what you find. Just let yourself go. Don't worry about the number. Don't worry about all the mathematics that you're hearing, but rather just understand the geometry that you're working with is actually your friend. So see it at that level if you're feeling overwhelmed at the mathematics that's here, but at the same time know that the math is there to further help you to understand what geometry is doing to benefit you as a creative person.
Very nice. Okay, then moving on to, again, this discovery that he made. He shows that in the next one. So now we're going to look at the 0.8541. On the left image, the green rectangle, 0.8541. He's showing that here on the bottom. And this drawing shows Mark recording this discovery that I talked about, the fact that if you add a square to this, well, in fact, note that the text in the upper right hand explains that adding a square under or over. Can you see that text well enough in the adding a square under or over the this overall rectangle AKMZ creates a triple golden rectangle. And then he draws that triple golden rectangle and says, "This is very cool," which I think is very cool. I love when he has these notes in the margins like this. Then he also shows a decomposition of AKMZ into 3 squares and 5 golden rectangles. In particular, the lower portion is a phi squared rectangle comprised of 2 squares flanking a golden rectangle. On the right, that's a root 5 rectangle, as Mark mentioned before. When you have a square and 2 golden rectangles, in this case they're stacked like that, that's a root 5 rectangle. And then the third rectangle that's sort of left over in the upper left, that is a different size square and 2 different size golden rectangles. So it's quite a lovely decomposition there.
See, I think this also shows you what I was just saying. This image does not look anything at all like the first image that you saw, the last one that you saw, because the golden section rectangle and the square are married. They love one another. They would never be separated from one another. So you can move them around, make them larger and smaller, and again, just have fun with them. That's basically what I try to do with a lot of the ratios that I work with. They're enjoyable, they're playful, they're relaxing. So.
Okay, next is called asymmetrical tiling in the 1.8541. This is on the wall in the museum as well. I added the letters for reference here. Again, this is an exact construction. There are 3 golden rectangles stacked on the left with a portrait orientation. I think you can see those. And then on the right bottom part, there are 3 golden rectangles stacked with landscape orientation, leaving a rectangle at the upper right. And then if we take AL to be 1, which is a fairly natural scale here, because that's the short side of the golden rectangle, then LZ will be phi, the golden section, the golden ratio, 1.618 or so. ZE will be, where am I? AK will be 3 phi. And then if you do the math, EM, which is the leftover piece up to the upper right, will be 3 over phi, which is the ratio that we're talking about, like in the United Nations building he was talking about, the rectangle on the right. So you have basically those 2 lengths in ratio. I'll put those in the lower right, make a rectangle. That is that rectangle that we saw, the 1.8541, which is the same as that. So those 2 rectangles are the same shape.
See, and you also notice on the right side, that's a vertical triple square. So that could just as easily be on the left side. That division between the 3 vertical golden sections that you see on the left side and the triple square on the right, that caesura, in music that's a break, that vertical break there is the golden section of the width of the rectangle. So you can even move that division. So for a lot of you that are just beginning to do your work and you're used to putting everything in the center of your rectangle in your painting or drawing or whatever it may be, just consider moving it about 10 or 12% left or right so that you're at the golden section instead of the middle. It automatically makes the piece more interesting. Not all the time, but a lot of the time. It's just another way of thinking about how you're making your composition. So.
Excellent, yes. Right, so if you, I didn't see this, Mark, as Mark is saying, if you take the 3 stacked golden rectangles on the left, just take those divisions over, that's a triple square on the right, exactly.
So let's just say you're doing a figure drawing. You're drawing a standing figure. Don't draw the figure in the middle. Move it to the left or the right a little bit and watch the difference in that composition on that sheet, on that page you're drawing on. Just that simple little difference.
Excellent. Okay, so further analyzing the leftover piece in the upper right-hand corner, so what we have there, it's 3 phi squared rectangles stacked. And each one of those is composed of one way is a golden rectangle with a square, or you can also do a golden rectangle the other way, flipped on its side with flanked by two squares, then if you take that golden rectangle, of course that's stacked there and there, that's the same shape as that. So there's lots of similar shapes going on there. And again, this is something that Mark loves in his constructions and loves to then highlight in his work.
It's a really beautiful way to tile the plane, to cover the surface with a pattern that goes beyond the traditional ways of using square or triangle, hexagons, and so on. This is just another way for, say, a textile designer or a fashion designer to bring pattern into the work. I mean, there's so much variety within this rectangular space. You know, you've got like 20 or 30 different possibilities that are there, probably more than that. But at least you have something that you can work from that's not so traditional, that you can bring this inventiveness into your pattern making. It's available for you.
Okay, so those were all exact relationships. We're going to move on to marriage of incommensurables. So what does that mean exactly? First, let's look at a long quote from Mark's artist statement for that 2015 pierogi show. And so Mark, it's on 3 slides. We're just going to read the first 2 and then some more slides and the third one. So
you want me to read that?
Please read that, yes.
My goal is to create harmony that resolves the initial numeric conflict. And my resolution is to draw the resulting compositional grid, a harmonic composition generated by the union of the 2 ratios, their shared unit, and the parts I select to join with straight edge and compass. You know, my goal is to try to get sometimes things that don't usually go together to go together in some way. Something that's rationally understood and some other parts that are irrational, and finding some way to link them. So that's what we mean by marriage of incommensurables, unable to be measured together. One of the things I try to do is to find a way to resolve that conflict visually and mathematically. And so that's the term marriage of incommensurables. That's basically what it means. It's just a challenge that I set up for myself visually and see if I can solve that issue, that problem.
Okay. So let's delve into that a bit further from a mathematical point of view. So incommensurability is related to the idea of rational numbers versus irrational numbers. So incommensurable is similar to irrational, but not quite the same. So first of all, any 2 fractions, which of course means a rational number, are commensurable because you can find a single number which measures both, commensurable. And you just use the common denominator, right? 3 and 7 is 21. 1/21 can measure both of those. 7 of those gives you the left one, and 15 gives you the right one. So those 2 fractions, any 2 fractions are commensurable. But any irrational number is incommensurable with a rational because there's no number which will measure both. It just can't be done. Okay? So there's no...
So just an irrational number means that there's a decimal place after the whole number, whatever it is. There's a decimal place, and then you see a series of numbers. When you see this 3 little dots, they're suggesting that the number goes on. That's called an ellipsis, by the way. There are 2 possibilities, maybe more. One of them would be 1/3 is 0.3333333. So if I ask you what you think the next number is, most of you would say 3, and you would be correct. But then if I say the golden section to you, I go 1.6180339885777 ... What's the next number? None of us know what it is unless we've been figuring it out with a calculator or something. That's irrational. That's something that gets on our nerves because we don't know what that next number is going to be. That's the difference between rational and irrational. It's just that simple.
I like that. I like that. Okay, what else? Not any 2, but here's 2 irrational numbers which are incommensurable. There's no common measure. But of course, if you had, a multiple of the same irrational, those are commensurable because square root of 2 will easily measure both of those. So it's a similar concept to irrational, but not quite the same. Now, you can have marriages. So Mark's idea is that he wants to be able to marry, for example, here, marry these two different irrational, these two incommensurable values with some geometric construction. And that can be done exactly. So there are possible exact marriages of incommensurables. And here's one. So this is a 6x5 grid. 6 to 5 is the minor third in music theory, and Mark has a whole series of minor third pieces.
Can I interject?
Sure, yeah.
This ratio is 5 units by 6 units. It's called the minor third, and supposedly it's one of the saddest sounds in music. And composers know this, and they'll actually use it in the composition that they're working on to make you sad. And then they'll find some other note at the end to bring you back to being happy again. It's called the minor third, and quite simply, if I have a string that's 5 units long, whatever the unit is, it is what it is. An inch, a meter, a millimeter, whatever it is. I have one of them that's 5 units and another one that's 6 units, and I rig them up onto a board and pluck them together, you'll hear that minor third sound. So that means that if somebody plays a chord on a piano and I look inside the piano and I see which strings are vibrating, I can take those strings out of the piano and I can make a rectangle from them. And that rectangle is based on music. This rectangle that you're looking at is based on music. That triangle that you see inside, there's a triple square on the left. You see it's diagonal, making the left side of that triangle. There's a double square on the right, and you see the diagonal of that double square. So it's really a triple square and a double square joined together to make this beautiful ratio.
And that constructs this triangle that Mark calls a Serlio triangle after the Italian Renaissance architect Sebastiano Serlio. And there are reasons for that, which we won't go into exactly. But it's a cool triangle. I didn't learn about this until Mark showed me. It's a triangle whose angles are the inverse tangent of 1, 2, and 3. It's kind of cool.
It's very cool.
It's very cool. And so here's an example of a construction that to find that, start with a square and a circle and find the midpoint of the square, bring it up, and then draw what you see there, and that's a Serlio triangle. So there's an example of, where are we? Here. So there's an example of a marriage of incommensurables, which is exact. So it marries these incommensurable values with an exact construction. Another example that we had in that Journal of Mathematics and the Arts article is this one. It's a trapezoid that has right angles on the right, and all of those values are exact. So there is a marriage of a bunch of different incommensurables. So they can be exact, or they can be approximate. And two of the pieces that you'll see in the exhibit here, this is Earth Tulpa, 2015, both of them are 2015, and Alchemical Still with Alembic, which is a chemistry pun, great one. Those are both based on a construction which is an approximate marriage of incommensurables. And so now we have the third slide from Mark's quote. So can you read this one?
Okay. And although the marriage is a vital component, the grid's the thing, for it is in the grid that manifests the relationship originally worked out. I love making the grids and having all the intersections coincide. For me, it's like making a map of the night sky. And another thing, in our human relationships, especially with people we love, sometimes you feel like they're being irrational and you're being rational, and you try to figure out a way to resolve the conflict. That sometimes enters my mind when I'm doing these works, because it kind of represents the human condition, the way that we interact with our fellow human beings. So this marriage of incommensurables is something we all share on a day-to-day basis with people we know and love. And this is just one example of that relationship, only it happens to be art and math. So
that's great. Okay, so here's the construction. All right. So first of all, this is an example of the. First of all, it's a square on the bottom start over. This is an example of what we saw before, the fact that the point 8541 plus a square is equal to the 1.8541. So this is exactly what we saw on the left here, right? The overall rectangle. And then, of course, we saw on the right, you have these stacked golden rectangles, and that's, of course, true here as well. There's 1, 2, and 3. Okay. So that's all familiar. But don't forget, Mark needs to construct this. So how does he actually construct this on paper? So he first needs a golden rectangle. How does he construct that? We start with a square, take half of that, and then half again in a triangular sense. And that's a right triangle. We can say that's a 1 by 2 by square root of 5, right? Pythagorean theorem tells us that would be square root of 5, the hypotenuse. So it's a right triangle with legs 1 and 2. Okay, then look here. You take that line segment as the radius. I'll do that again. There it is. Put your compass point at P. Draw that arc. And now take that line segment as your radius. Put your compass point at Z. Draw that arc. And that gives you a golden rectangle.
Bingo.
And then you have 3 of those. Okay? But then what he realized is if you start at that point C, which is the upper left-hand corner of the square, about in the middle of the left, you'll see a C. If you put your compass point there and then use that as your radius and swing it around, it lands almost exactly at the top of the rectangle. And Mark did this several times, and he does his constructions. He sharpens his pencil before, he does his pencil first. He sharpens his pencil before every single stroke, whether it's a line or a circle. And every single time it was landing right on it, which to him makes him think, okay, this is exact. And then he calls me and says, is this exact? And I check it out, and it wasn't. But you know, when it comes down to it, but it's still cool. In fact, at the Bridges Conference in 2017, I was surprised to see a lot of the mathematicians in the audience liked the approximate constructions even better, which is, for me, that wasn't the way I thought of it at first.
No, see,
Go ahead.
I get paranoid when I'm doing my work and I think I've got something. I really want to make sure that some mathematician in the year 22, 23, doesn't come into my drawing and see that I wasn't right. So I want to make sure if I make a claim that I'm on the money. So I always call Steve and get on his nerves by asking him to prove what I just did to make sure that it's right, so I can go around and kind of get an attitude like, wow, look, check out what I just found. So.
You don't get on my nerves. I love it. I like it more when it's exact, but everyone can have their own opinions, right? But more importantly, realize anything in the real world is approximate, right? Mathematicians live in an ideal world where the square root of 2 is this ideal thing. But if you actually try to measure something, you can't measure exactly the square root of 2 ever. So everything is approximate if you're building a house or a bridge or making a construction. But the important point is that up to the accuracy of whatever you're doing, it's as good as exact. He could, if this were exact, it wouldn't act any differently when he did his construction. You see? So that's what this is based on, this grid is based on, and that's what that work is based on. Again, that's Earth Tulpa.
See, the challenge always is, how do I take the number that's manifesting? Geometry is a visual presentation of number. And then I get this grid. How do I make it beautiful? And believe it or not, like one of the biggest challenges is to bring color into a graphite or pen and ink drawing. And plus I don't ever want my drawing to look like a geometry coloring book. I don't want it to look like I just filled everything in with a crayon. So that's always the underlying challenge for me once I get past the geometry challenge. It's the color challenge that always drives me forward to try to make the piece as beautiful as I can. How do I make geometry beautiful beyond its original geometric beauty? So.
And the last one here, again, this is alchemical still with alembic. I think you can also see, he was talking about like stars in the night sky. Looks like almost there's a horizon there, and then the upper part is the night sky. Anyway, that's our presentation. We welcome any questions at all.
Thank you.
Thank you.
Thank you. Thank you. Thank you for coming. I think that's just so wonderful, and I have to say, Janine said she really wanted to get the math department into the art department, and let's hope the opposite is true too, that the art department goes to the math department. Collaborating with another field of endeavor that you don't really have an affinity for originally may be a really great step for you to take. If you're afraid of number or whatever, maybe buddy up with someone in the math department and just start talking about what you're both doing. You're both working with number. And I think it's really a wonderful thing. What Steve and I are showing all of you is hopefully a successful relationship between an artist and a mathematician. And it doesn't have to be art and math, it could be math and music or whatever. But I think it's really valuable, especially in this day and age, for young people like most of you are, to really give some thought to collaborating with another individual so that you're not in this process, this pressure of coming up with original creative work, but you're stuck because it seems like so much of it has already been done. Maybe there's a possibility of you finding something in your own work, take a step back and look at it, that may involve some number in some form, where you might have a common link with someone in the mathematics or in the sciences that you may collaborate with, and who knows what's going to happen. Because once you start collaborating together, you feed from one another. You give each other ideas, whether it's intentional or not. You give each other ideas, and then you go back into your own discipline with a new sense of purpose in what you're doing. And I think that's the lesson that I hope all of you take with you tonight. Stephen and I really love one another, and what we each do individually and together, that's the message we're trying to send. Like, open up a little bit, if you're not already, open up a little bit and see what's possible with someone or something that seems to be the opposite of where you're at right now. So. No.
Great.
Questions in the audience?
How do you ask a question? Right? I mean, with what we showed you, how do you form a question about all this, right? I fell in love with geometry long ago. I won't tell you how old I am, but when I was in art school, everybody loved Andy Warhol. But I secretly loved Leonardo and Raphael and Renaissance painters, and everybody made fun of me, come on, Mark, get modern, But somebody told me that there are geometric compositional grids underneath of Renaissance paintings. Not only that, but the geometry that was used had spiritual and philosophical and symbolic meaning. Once I learned that I found out about that, there's a book called The Painter's Secret Geometry. Once I knew that was true, it just completely changed everything that I was planning to do with my career as an artist. And I just fell in love with geometry, and I still am. So you just keep your eye open for what might be out there. So, yeah.
All right. Well, if there aren't any questions, maybe we should go eat cookies or something and go see the exhibit.
Yeah. So Stephen and I will be here. If you have a question, but you feel like you might get embarrassed if you ask it in front of a group, we'll be here. And I'm ready for any question you want to give me. So, thank you again for coming.
Yes,
I love
thanks
you
for
all.
coming.
Thank you. Peace out. Good job, Steve.
Yeah.